look at that as a fundamental value. That's always the play between acid and base is occurring in that reaction. If we look at this, this really is 1 times 10 to the minus 14 equals H2O plus OH minus. Remember that they're made from the same reaction, so they have to be the same number. So if we wanted to find out what either of them would be in order to equal out to 1 times 10 to the 14th, you'd find that H3O plus equals OH minus equals 1 times 10 to the minus 7. That's at neutral, when you have an equal amount of acid and base, that's the value that they would take. The take home, the reason we worry about autoprotolysis of water anytime is because it doesn't matter. When it's pure water, those two have to equal 1 times 10 to the minus 14. When we add an acid or base to water, the only thing that's going to shift is that ratio. How much H3O plus is there, or how much OH is there. It always equals, in the end, that constant. That constant is going to become really important because it's going to tell us if we know an acid or base amount, we can find the other one based on that reaction. They have to equal 1 times 10 to the minus 14, the fundamental quantity. So even when an acid or base gets introduced to water, the only thing that changes is the concentration.
Where did you get the 7 again?
Now, basically what I did was, these are both the same number, so if we call these both x, it'd be x squared. I took the square root of that number, and that's what it goes. Let's look at example 15.2 to use this expression. On 15.2, they ask us to find the following. They tell us in 15.2 equation is 8.2 times 10 to the minus 10. And they want to know what is the acid concentration. So again, this number is going to become important because it's a link. If you know OH minus or H plus, you can find the other one because of that expression that we have there. The expression tells us that Kw equals this times this. We always know what Kw is. 1 times 10 minus 15. We don't know what H3O plus is. We do know that hydroxide we can solve for H3O plus just by dividing both sides by 8.2 times 10 to the minus 10. If we do that, we get that the hydronium ion concentration is 1.22 times 10 to the minus 10. Again, that number, or that general idea, we will use over and over again. If I know one, I can find the other because of that simple relationship. The ratio of acid and bases will change. The product always works out to be 1 times 10 to the minus 14. That's unchanged. You can see that this is a very small amount of base. On that scale, that's a fairly large amount of acid, minus 5th versus minus 10. Acids and base essentially are either on par when everything's equal, whereas one goes up, the other goes down, because we're always equaling the same number, just a ratio of the two that are fluctuating. We measure acids and base by the pH scale. scale is our way of measuring acid and base. We've done it in a lab enough. We've taken a pH probe and put it in a sample. You know how that works. Mathematically, though, the P part of this is a power function. The power function tells us that the power of the hydrogen ion is the negative log of the hydronium ion concentration. The reason the negative log is there is because when we look at concentrations, concentrations can be all over the board. It's hard to judge or assess a number. By taking the negative log of a concentration amount, we make it an integer value. We make it a number that we can look at very easily. Is it 1, 1.2, 12.4? We takes this and makes it a number that is easy to look at. That's why we do the negative log idea. Conventionally, most books say pH runs between 0 up to 14. There are negative pHs, but the conventional scale goes 0 to 14. When we look at the pH scale, we look at what happens. We look at 3 areas. Look at 0, 7, up to 14. On this side, we have the extremely acidic range, neutral at 7, and at the other end, we have the base side. If we look at that conventionally, we have on the acidic side high amounts of H3O+. In the middle, we have as much H3O+ as we have OH-. Now on the base side, we have virtually no or very low amounts of H3O+, but we do have high amounts of the hydroxide. We could also say over here, if we look at that just on the scale side of things, we go from all acid to an equal amount to all base. The power function here isn't restricted to the hydrogen ion. We have power functions for any species we can look at. This is the one everybody knows, but there are other ones. The other one that falls perfectly in line here is the POH. POH is another power function. And POH, if this is negative log hydronium ion concentration, this guy, negative log hydroxide ion concentration. It measures the same thing. It measures how much hydroxide is there. One thing that is useful is that these two numbers, pH and POH, without going through the derivation, if I take those two numbers, they have to add up to 14. That will become useful in a couple minutes. Finally, when we looked just a minute ago at the KAs, Ka numbers can be very small, they're all over the board. One last power function that's useful we can have pKa. Power function says it's negative log of the Ka. Again, the only reason we do that is because it gives us numbers to look at. We can look at much easier, more easily, a number that is an integer value than looking at a number that's something very small. Just remember, if you're dealing with a pKa, the smaller the pKa is, they gave you two acids and two pKa's, and they asked you to assign it. The smaller the pKa is, the stronger the acid is. The reason that's opposite of what we saw with the K's is because we took the negative log of it, changes the sign. So if they give you two acids and two pKa's, just look at the pKa's, look at those numbers. The one that has the smaller number is the stronger of the two. We'll see pKa values later on, especially in chapter 16, we start to use them quite extensively. There is, tucked away in the back of your book, they put them, nope, they moved them out, never mind. Disregard. It's in the table in chapter 16, not in the back. So, if you have two acids, you need to compare them. Just look at the pKa values. The smaller one is the one that wins. So you'll see some homework problems that ask you to compare an acid based on Ka or pKa. Just remember, once that negative log's there, flips the relationship. Questions? Let's take a look at two problems that relate to using these couple equations and one more that we're going to derive. We're going to divert from the book a little bit on the way they solve one of the problems. Let's look at 15.3 on 709. Says the hydroxide ion concentration 7.1 times 10 to the minus third. They want you to find the pH of the solution. When you look at these problems, in order to solve for the pH, I need to know how much acid's there. But all I know is how much base is there. So we're going to employ the first equation. Said that autoprotolysis constant is these two multiplied by one another. So if I know Kw and I know hydroxide, I can find H3O plus directly. Times 10 to the minus 14, OH minus 7.1 times 10 minus third. H3O plus is our unknown. Pretty quick to get that number, just divide by the 7.1. The number works out to be 1.4 times 10 to the minus 12. So that's the concentration of the acid, but they don't want concentration, they know it's pH. Once I know that, second equation, pH, negative log, H3O plus. I can take that number I just found, plug it right in. pH of that is 11.85. A couple things about the numbers. If we look at this, remember the rolling number, we're talking about everything adds up to the minus 14 power. This one here is to the minus third. There's a lot of base hanging around there. A lot. Very, very large amount. It tells us the amount of acid has to, remember they teeter between